Hello students, I hope all of you are doing fine. Today we are going to discuss about a different type of Boolean expressions, and we have seen in the last classes a Boolean expression can be expressed in different formats. We have seen Boolean expression in SOP form, that is sum of products form, and some expressions we have seen in POS form, that is product of sum form. And we have also seen the cardinal form of a Boolean expression and the canonical form of a Boolean expression, right? So today we can discuss more detail about this different type of Boolean expressions and its representations. Okay, in the given table you can see that we have different type of Boolean expressions. The first one, that is f is equal to a dot b plus a dot b bar. So we can say the type of expression, the first one is an example of a canonical SOP form, that is canonical sum of products, right? So you can see that a dot b plus a dot b bar, which is a canonical SOP form. And whereas in second expression you can see that f is equal to a dot b plus b bar. So a dot b bar plus b bar, actually this expression is in SOP form. We can say it is in SOP form but not in the canonical form. How we can say that this is not in the canonical form? Because we can see that there are two product terms, that is a dot b plus a dot b and b bar is the two product terms in the given expression, but that b bar doesn't contain, b bar is a lone term, it doesn't contain the value a. So we can say even though this expression is SOP form but it is not in the canonical form. Please refer the definition of canonical form in the textbook, right? An expression is said to be in canonical form if its terms contains all the Boolean values. So in the first case f is equal to a dot b plus a dot b bar. In that one two product terms are there, a dot b and a dot b bar. So in both a dot b and a dot b bar, both Boolean values a and b are present there. In the case of the second expression, what you can see, a dot b and b bar, and a dot b we have both a and b bar it is missing a. So we can say it is not in the canonical form. Now the third expression you can see that it is the POS form, that is the product of sum form, and there are two sum terms in the third example, that is a plus b and a plus b bar. So all the Boolean values are there in two terms, that is a plus b, both a and b are there, a plus b bar, both a and b are again there. So we can say it is in canonical POS form. Now see another example, that is example number 4, f is equal to a plus b dot b bar. We can say this expression is in the product of sum form but not in the canonical format. So POS form means, see there are two expressions, there are two terms, that is a plus b and b bar. So in the second term, that is b bar, a is missing. So we can say that it is in POS form but not in the canonical form. Then example number 5, you can see the cardinal SOP form, and so I am using the sigma symbol or summation symbol to represent the SOP expression. And example number 6, you can see f is equal to pi of 1, 2, 3, which is in the cardinal POS form, that is a product of sum form. Okay. Here now we are going to see how we can convert. Suppose an expression given is in the sum of products form but not in the canonical form. So there are some steps to convert a sum of product expression into its canonical form. Okay. So we have different steps. Please read the given steps in the video. The first one is we have to check the missing variables in each product term. Second one, perform AND operation with terms which have missing variables. Third one is expand all the terms and remove the duplicate terms. And fourth one, that is the once we remove the duplicate terms, the produced SOP is in the canonical form. So I can explain that with the help of an example. Okay, here you can see an SOP expression is given. That is, a Boolean expression is given. The given expression is f is equal to a dot b dot c plus a dot b bar plus a dot c. So we can clearly see that this expression having three product terms, that is a dot b dot c is the first one, a dot b bar is the second one, and a dot c is the third one, right? So this expression is clearly not in the canonical form, because when you consider the second term a dot b bar, where the term c is missing, and consider the third term, that is a dot c, in a dot c b is missing, right? So we are going to see the how we can convert this SOP into its canonical form. So our step number 1 is that we have to check the missing variables in each term. So the given expression is f is equal to a dot b dot c plus a dot b bar plus a dot c, right? So the missing term here it is in the first term, that is a dot b dot c. All the Boolean values are there. In the second one, a dot b bar c is missing, and in the third a dot c b is missing. Now what is the second? We have to perform an AND operation with the terms which have missing variables. So we have to perform the AND operation. Now see the step 2. F is equal to a dot b dot c plus a dot b bar dot. We are performing an AND operations with the missing variables. So actually we know that in Boolean algebra c plus c bar is equal to 1, right? So a dot b bar dot 1 can be replaced with c plus c bar. Now the third term, so where b is missing, that is the third term is a dot c. So b is missing. So we can perform the AND operation with the b, that is a dot b plus b bar dot c. After that, step 3 is we have to expand. So f is equal to a dot b dot c plus, now we have to expand, that is when we expand a dot b bar dot c plus a dot b bar dot c bar. Again if we expand the third one, we will be getting a dot b dot c plus a dot b bar dot c. Now our next step is we have to remove the duplicates. Once we remove the duplicate, we will be getting f is equal to a dot b dot c plus a dot b bar dot c plus a dot b bar dot c bar. And step number 4, that is after removing the duplicates, we are getting the expression in the canonical form. So a dot b dot c plus a dot b bar dot c plus a dot b bar dot c bar is in canonical SOP form.